Welcome to this third colloquium of this new series. Today we have Paolo Criminelli from ICTP. You will see the title there. And my only additional piece of information, I hope it's correct, there should be refreshments at the end in front. There's not a clear evidence yet, but they are supposed to be there. So my colleague Enrico Trincherini will give a brief introduction.
So it's my great pleasure to introduce today's speaker, Paolo Criminelli, although I'm sure he's very well known to many of you since he spent 8 years here at Scuola Normale, first as an undergraduate student, then as a PhD, working with Riccardo Barbieri. And after the PhD, he moved to Harvard University, where he got interested in the physics of the early universe. That is the topic he will talk about today. And in particular, in a series of papers with Mattias Zaldariaga and other collaborators, he described a way to characterize observable signatures of the accelerated expansion of the early universe. And this series of groundbreaking works were later recognized with the 2011 prize from the European Physical Society. And let me read the motivation. Paolo was honored for his contributions to the development of a solid field-theoretical approach to the early universe cosmology and for his studies of non-Gaussianities in the cosmic microwave background. And after 3 years at Harvard, he moved to ICTP, where he now serves as the head of the high-energy cosmology and astrophysics section. And at ICTP, following in his advisor footsteps, he dedicated a lot of time to mentor with passion and rigor a new generation of scientists, and as a result, some of his former PhD students are now young leads in our field. So you didn't come here to listen to me, so please join me in welcoming Paolo. And he is known for his clarity as speaker. He promised to deliver today a talk that will be understood by everybody, including my 9-year-old daughter who's watching online. So, no, I'm joking. He's good, but not that good. So, thank you, Paolo.
Okay. So, thank you very much. It's always a pleasure to be back in Scuola Normale, and thanks for the introduction. So, yes, I will try to be. I mean, it's a colloquium, and so my goal is to be understood by a broad audience. So, please. Ask me questions. I'm not sure if my high-energy colleague will learn much from this talk, but the goal is to describe basically where we are, in a sense that you probably saw these things in many occasions, but I would like to put emphasis on how much of the story I'm going to tell is based on experiment, how much is a story, so what is the status and the prospect of this field. So the topic is the early stages of the universe, and in particular, what are the initial conditions of our universe. So first of all, we need the initial conditions for cosmology because the universe is dynamical, and the observation of a dynamical universe goes back to almost 100 years ago. This is the work of Hubble. And the basic observation back then was that you look at galaxies and you observe the Doppler shift of these galaxies. So you measure the velocities of these galaxies, and you can plot the velocities and you plot the velocities in the vertical axis as a function of the distance, and you get an approximately straight line. So these are the first data Hubble. So the picture is that looking at galaxies around us, you see that they are, on average, flying away from us. Notice that this kind of measurements is still very popular nowadays. So we still measure the expansion of the universe looking at similar data. Actually, nowadays there is some tension between this kind of measurements and other measurements. These are called Hubble tension. But this is the beginning of our story. So the universe is dynamical, it's expanding. So what does it really mean, expanding universe? Okay, and why it gives this proportionality? So if you think about having some Euclidean space, like a tablecloth with regular squares, and you imagine that these are two galaxies on this tablecloth. If you stretch this plane, the distance between galaxies will change, and you can easily convince yourself that the velocity will be proportional to the distance, because in a given time, let's say everything doubles, and so the velocity that you measure is proportional to the distance, which is what Hubble was observing looking at faraway galaxies. So usually we think about the expansion of the universe as something associated with general relativity. I mean, you can also think about it very easily Newtonially. In a sense, imagine that you don't know general relativity and you want to describe the evolution of the universe. So you're going to have galaxies which interact by the gravitational interaction. And if you, so this equation, which in general relativity goes under the name of Friedmann equation, can also be understood Newtonially. So this is the kinetic energy, and this is the potential energy, which of course is negative. And this equation just states that the sum of kinetic energy and potential energy is just a constant. Okay? So I'm just saying that although the correct description is the one of general relativity, you can also think about the expansion of the universe just saying that if I have some self-gravitating matter, what we are observing is that the universe is expanding, so the galaxies are going far away from each other, but they attract, and so the expansion is decelerated. Okay? So I think that general relativity just gave the momentum to really try to study cosmology, but even Newtonially you can write equations which are quite similar. So if you accept this, that the universe is expanding and the distance among galaxies is increasing, then you can extrapolate and say, okay, let me widely extrapolate. Let's go back in time. If I widely extrapolate, at a certain point, all matter in the universe will be very, very condensed, with very high density. And at a certain point, I expect a very hot state. Of course, this is a very wild extrapolation, but let's see if experiments support this. Well, if you go very backwards in time, at a certain point, the temperature of your plasma, so all matter is more and more concentrated, so the temperature rises, and at a certain point, the universe will be a plasma of electrons and nuclei, so there are no atoms, everything is ionized. And in this state, photons, they scatter on the ions, so there is no they cannot travel, so they are trapped inside this plasma in the same way it happens inside a star. Then, if you go forward in time, at a certain point, the temperature drops and the atoms form. This is called the recombination in cosmology. And the difference is that at this point, photons can travel, so they interact much less with atoms, and so they start propagating approximately freely. So let's see what we should observe. So if I observe a certain direction in the sky, since the light travels at a certain speed, if I really look very, very, very far away, at a certain point, the light that I receive now comes from an epoch of the universe where the universe is in this ionized form. Okay? So what you expect is that to receive light from what is called the last scattering surface, which is this surface over here. So I receive photons, light, exactly as I do looking at the sun. So I receive light from the surface of the sun, which is, so inside the sun the photons are in equilibrium with the rest of the plasma, then at a certain point they are released and they come to us. The only difference is that now I am inside, so I look at around in the universe and I see this surface from which photons are released. Okay? So this is what you expect, at least theoretically. But this is also something that is observed, and this is one of the pillars of the Big Bang cosmology. So the first detection of the cosmic microwave background goes back to Pezias and Wilson, and you might know that this is a completely serendipitous discovery. They were looking for they were using this antenna for telecommunication, but they observed a signal that they couldn't remove. And so it was pretty funny because, they tried to remove it in all possible ways, and at a certain point, somebody told them that, it might be that this is the radiation that we expect from the Big Bang. So they called Princeton, which is this in New Jersey. So they called Princeton, where a group capitainated by Dickey was actually thinking about making an experiment to look for the cosmic microwave background. So Dickey received this call, and apparently at the end of the call he said, we were scooped by this discovery. So it's so we were so the experiments. This was the first experiment detecting the cosmic microwave background. The cosmic microwave background is a thermal radiation with a temperature which is about 2.7 Kelvin. This was the measurement back then. Okay, this of course is a key step. So this extrapolation from the expansion of the universe to a thermal state, it works because we see that there is this remnant of the thermal radiation. Okay, now what do you do? Well, we try to study it better and better. Okay, so first of all, you try to measure the temperature in all directions to see whether there is difference between one place and the other. And what you find is that there is no difference whatsoever. Okay? So for many, many years, between 1965 and 1992, better and better experiments were trying to measure the difference between the temperature in one direction in the sky and another direction in the sky, but there was absolutely no difference. So the map of the universe was homogeneous like this, okay, for many, many years. So this is the first step. So the temperature is remarkably homogeneous around the space. Then finally, in 1992, pushing better and better, with better and better accuracy, at a certain point, they were able to measure small differences between one patch in the sky and another one. So these are small differences of the temperature of the cosmic microwave background. The typical fluctuation is of order 10 to minus 5. Okay, so compared to the homogeneous background at 2.7 Kelvin, there are extremely tiny differences of about 10 to minus 5. Okay? Okay, this is a beautiful map, but it's a map that is limited by experiment. In a sense, you see that it's, there are these blobs, but the size of this blob is because the resolution of the experiment was not good enough. So of course, what you try to do is to improve the experiment to see the structure of this map on finer and finer scale. So basically you put on your glasses, so you have a better experiment. And so this first experiment was, you should think as a pair of glasses with a cost of 150 million. It's a quite cheap experiment for the high energy standard. And it's called WMAP. So it's a better map of the universe. You see, I want to stress, it's the same map, you see, it's the same map, but with better resolution, okay? Because, okay, the temperature is, so we are measuring the temperature in the sky in different directions. We are basically mapping from the inside the temperature of this last scattering surface. Okay, but still not enough, so you can do better than this, so you put even better glasses, $700 million, and this is called Planck, and this gives a even better map. Again, it's the same map, but with higher resolution. Okay, this was launched in 2013, and basically it finished in 2018. Okay, so this is the best map, at least the best complete map of the sky that we have at the moment. There are, as I will say, there are better experiments looking at some regions in the sky, but the overall map is this is the status. Okay, sorry, go back. So what should I learn? So now I have this map. I know there are all these features. I remind you that it's almost homogeneous, but there are very tiny perturbations. So the first thing that you do, you basically look at a Fourier decomposition of this map. So you look at the signal as a function of, these are the multiples over the sphere, or the angular scale, if you prefer. And you see these bumps. You see these acoustic bumps. What is the origin of these bumps? It's just that, I remind you, what are we describing? So back then, there is a plasma of electrons and nuclei, which are going to recombine to give atoms. So you expect that it's a plasma which supports acoustic waves, okay? And this is exactly what you measure, okay? So these features are associated with these acoustic oscillations. So I want to stress the following. So the CMB is really a wonderful system for physics because for two reasons. So first of all, when you want to study a physical system, you like to use perturbation theory. And as I said, this is a beautiful perturbation theory because the perturbations are very tiny, 10 to minus 5. Okay? So when you want to do perturbation theory, it's very nice to have a parameter which is very small. So perturbation theory is very accurate. People even went to second order in perturbation theory, but we're already talking about something which is over the 10 to minus 10. This is, so it's a system which is very amenable to perturbation theory. And on top of this, it's quite simple physics because, well, I told you that we are talking about atoms, hydrogen and helium atoms, that they recombine. So it's not that it's physics that we don't know. Okay? So everything is completely under control. And indeed, this is a source of many information. So for instance, looking at the ratio between one peak and another, you can measure quantities that describe the composition of the universe, so how much photons there are compared to protons, these kind of cosmological parameters. Okay? And everything can be done basically analytically because of the simplicity of the system. So now, let's go back. So what is the picture? So I look at the very early universe. I see very tiny perturbations. And what happens to these tiny perturbations? Well, there is gravity. So you expect that these tiny perturbations will increase because a region which is a bit more dense will attract what is around. So it will form a structure. And indeed, this is what we can simulate. So, of course, there are experts here in the audience. But the picture that I want to convey is that starting with very tiny perturbations in the very early universe, under the influence of gravity, you form this very nonlinear structure, which of course include clusters, galaxies, planetary systems, and the Earth. So this is not a topic I want to discuss, but this is a story that we know quite well. Of course, not all the details are completely understood, but the qualitative picture is completely understood. So we understand that the universe evolves from this very homogeneous state with tiny perturbations and evolves structure that we observe now in the sky. So this is another picture of the same thing. So from the CMB, so I'm here, I'm observing the universe. If I go very far away, I see this surface very far away, and then closer by, there are structures that evolve. Okay. So the topic now is to discuss what give rise to these initial perturbations. Okay? So now we observe that there is this early universe with this plasma with tiny perturbations. Okay, what is the origin of these perturbations? So this is the topic. So in some sense, it's like asking, like the Cauchy problem of the universe. So I want to discuss why there are these initial conditions that give rise to our evolution. So it turns out, as I will explain, that these initial conditions appear quite finely tuned, very particular. In what sense? Well, first of all, what we observe, as I said, is that the temperature or the energy density is remarkably homogeneous as I look at different directions in the sky. And also the composition, by composition I mean that in one direction in the sky, in principle, there could be more baryons than in another direction. But not only the temperature, but also the composition is the same in different directions in the sky. So it's completely, is very close to homogeneity. So one question is, so why it is so homogeneous? And another peculiar feature of these initial conditions has to do with the initial velocities. So let me maybe go back in this way. So if I go back to the original Friedmann equation that I was describing, so you remember that there is this constant kappa. So basically this constant kappa, you can think is the integration constant of the energy. So the same happens if I throw a stone in the gravitational field of the Earth. So this constant will decide whether this stone will fly away from the Earth or will come back. Okay, is the total energy of the system. It turns out that this constant is very close to zero. So it's like we choose the initial velocities of my galaxies in such a way that this constant is like saying that it's finely tuned to be between the stone comes back and the stone fly away. It's really borderline. These two paradoxes, these two disturbing properties, they can be better defined using relativity. Because in relativity, of course, we know that the speed of light defines a maximal speed to communicate information. So now it becomes very well defined. So the first problem is the following. So let me repeat. So we look at this direction in the sky and this direction in the sky. They have exactly the same temperature up to 10 to minus 5 corrections. But I can also calculate this small circle, which is the space that light could travel from the beginning of the universe since until the emission of light. Okay? So the universe at this point was very young, and light could only travel from the center to this radius. So in other words, there is no possibility to send the signal from this point to this one. So the question is, how is it possible that I observe the same temperature, but there was no communication between these 2 points? The second feature, which is why this constant k is so small, in general relativity, for the experts, this k is also interpreted as the curvature of space. So sometimes it's called the flatness problem, because in general relativity, the fact that k is very small is the same as saying that the spatial surfaces are very close to spatial flatness. Okay, so until the 80s, people were living with these particular initial conditions. But you know, these are the kind. I mean, there's nothing conceptually wrong in these initial conditions, but they look a bit strange. Until the 80s, when starting from Alexei Starobinsky, Alan Guth, Andrei Linde, the concept of cosmic inflation came into the game. By the way, Starobinsky passed away a few months ago, so it's good to remember his important contributions. So what is inflation? Okay? So okay, there are various ways to describe it, but let me say the following. So this is the evolution of the universe, so this is time, and this is the expansion of the universe. The standard evolution is given by this curve over here. Okay, it's an expansion which is decelerating. Well, gravity is attractive, so it tends to decelerate the expansion. Okay? So this is the normal evolution of the universe that we expect to take place. So inflation, in some sense, buys some extra time. So in a sense that instead of having a decelerated expansion, I have a period of accelerated expansion. So meaning that the second derivative of the scale factor A is positive. Okay? So why this extra time is important? Well, because it solves the problem that I was discussing. Because, well, the first problem, I remind you, is related to the fact that I don't have time to communicate with this other point. But if the universe has a bit more time, I mean, a bit more, okay, I put this number just, I mean, we don't know this number at all, but I just want to stress that it's very small compared to the age of the universe, but I need a bit of extra time in order to solve this homogeneity problem. Okay. I can be more quantitative, but it doesn't matter. So I need a period of accelerated expansion. This period also solves the other problem, because, well, this is easy to see, because if the second derivative is positive, means that this is increasing in time, but then if it increases while k is a constant, well, then it makes sense that this constant is small nowadays, because there was a long period in which this increases and k remains constant. Okay, this is looks a bit okay, artificial. Okay, so what is the problem? Well, the problem is how do we make the universe accelerate? Gravity is attractive. So in general, the first thing that you expect is that whatever I do, I have an expanding bunch of particles. They attract each other, so they try to slow down this expansion. Okay? I want to do the opposite. I want to accelerate. The catch is that Newtonially, what sources gravity is mass. When you go to general relativity, and in this general relativity, of course, is crucial, not only mass sources gravity, not only energy source is gravity, but also pressure enters in the equations of general relativity. So this is the equation that you might have seen, so the Einstein's equation. The left-hand side describe the curvature of space-time, or more prosaically, gravity. The right-hand side describe matter. So this is a matrix, and this matrix contains mass, so this is the mass density, rho, but also contains pressure. Okay? So the first message is that, well, I don't know if gravity is attractive or not. It depends on what is rho and what is p. And it turns out that there is a very strange form of matter, or very strange form of energy, that has a negative pressure. And it is just, so let's imagine to be in a metastable state. Okay? So whatever is your system, instead of being in a vacuum, you are in some metastable state. So you are sitting on top of some constant in the potential. So usually, if you're not interested in gravity, this constant is irrelevant for the discussion. But in general relativity, all forms of matter gravitate, and even this zero energy is important. And it turns out that this energy of sitting in a metastable state has negative pressure, and this negative pressure is what makes the universe accelerate, or it can. It's a candidate to make the universe accelerate. So you can ask, what does it mean to have negative pressure? Well, it's not. So one way to see it is that this constant that I'm sitting. So imagine that I'm sitting in this state. So the energy density in this state is a constant. So it's a strange form of energy that even if the universe is expanding, it does not dilute away. So if you think about it, if you want something like that, when you dilute it, it does not go away, it means that in some sense it has a negative pressure. Okay? So if you take, for instance, a gas, the pressure will be positive and the energy density will go down as the universe expands. Okay, so sorry, this is a bit of a technical slide, but I just want to flash it. So more technically, what do we mean by inflation? So this is a candidate, it's the simplest model of inflation. It's called slow roll inflation, and the idea is similar to what I was saying. So imagine that, so I want to be sitting, to be here, sitting in a metastable state, so that this energy will drive an accelerated expansion of the universe. So this phi is a scalar field. So you can think about it as the electromagnetic field, but with the only difference is that the electromagnetic field is a vector, so it has a polarization. Here it's a scalar, does not have a polarization. We don't know what it is, so we call it the inflaton. It's a field. It's similar to the Higgs as another scalar particle. And this scalar, we postulate that it has a potential which has a... so I said that I want to stay in a metastable minimum, but I also want, at a certain point, to finish this period. So the idea is to be in a situation which is, for a while, you evolve over this plateau, and this energy drives the expansion of the universe, and at a certain point, you reach the minimum, and you give rise to what I was saying before, the CMB, and the structure formation, and so on and so forth. So this is called reheating in cosmology, so it's the process by which this energy is converted into plasma, into standard model degrees of freedom. So I need this potential to be flat, in order sufficiently flat, this can be quantified, but I don't want to enter into details, but I need a very flat potential in such a way that I stay for a long time in this metastable state. By the way, you can convince yourself that if you use the equation I had in the first slide, and you put a constant energy given by this, so this lambda becomes a constant, and the solution is an exponential expansion, which is exactly something like this. So something with in which there is a second derivative which is positive, so an exponential expansion of the universe. So it's useful to think about inflation, at least in this model, as a period in which the expansion of the universe is exponential, so with good approximation. Okay, so this is, so now, so bear with me, so I will later discuss why we, so now I'm telling you a story, so then I will try to say what we know experimentally about this story. But let me, first of all, complete the story. So if you continue like this, so if you look at this picture, so you have this exponential expansion, but if you wait long enough, the universe becomes completely homogeneous and flat. Okay? So it's true that we solved the problems that we were discussing, but even too much, because now we come back to the same problem. So now we erased all the initial inhomogeneities, and we are left, okay, but we don't see a completely homogeneous universe. We see a universe with small, tiny fluctuations, okay? So what is the origin of these tiny fluctuations? It turns out that in inflation, the answer is already in the equations, so I don't need to do anything else. And the answer has to do with quantum mechanics. So what I said here is completely classical, so I'm looking at this field which is evolving, but as you know, quantum mechanics will introduce quantum fluctuations, and let me try to explain the logic. So there is nothing very fancy, so sometimes it is described in a very fancy way, like in an expanding universe, we don't know what is the vacuum, and so on and so forth. But I think the simplest way to think about the problem is the following. If you go back to this slide, and you look at this field, phi, I decompose in Fourier modes, so I have all my Fourier components of phi. So in first approximation, these are just harmonic oscillators, quantum harmonic oscillators. Okay, quantum harmonic oscillator is the simplest problem that you do in quantum mechanics, but here there is a catch, because the universe is expanding. So there is time dependence in the system. So you have to take all these Fourier modes, which are harmonic oscillators, and you have to take into account that the parameters of these harmonic oscillators are evolving in time. And so, so you have your harmonic oscillator in the vacuum, so this is the usual Gaussian, which is the ground state of the harmonic oscillator. But the universe is expanding, which is the same as modifying the potential of the harmonic oscillator, and therefore this process leads you to a state which is not the vacuum. Okay? So this is what when we say that quantum fluctuations generate the structure that we see in the sky, we have in mind this. We have just in mind the fact that the small vacuum fluctuations are amplified by the fact that the universe is expanding. Okay, so this I think it's a remarkable statement, and I think it's very nice way to introduce the initial conditions of the universe. So this is a quote by Dirac that basically, well, you can read it, but is asking how to put initial conditions with the new cosmology, so the cosmology in which there is an evolution. And he realized that, classically, we observe a lot of complexity around us. So if I want to put initial conditions to map to the complexity that we see, we have to put a lot of complexity in the initial conditions. But if you think there are quantum fluctuations, this complexity is just inherent in quantum mechanics. Okay. So of course, I don't want to enter too much into details, but of course you know that quantum mechanics is very disturbing, and in particular, notice that what we are saying is that the reason why the Milky Way and our solar systems formed here is because there were a particular quantum fluctuation that give rise to us, and So for instance, you can ask, are the universes in which there were other quantum fluctuations, they do really exist? So this is a typical question in quantum mechanics, but applied to the whole universe, which is a bit more disturbing. So this is the story. But okay, so far it's a beautiful story, I think. It's a beautiful story in a sense that it's potentially it's an explanation of the beginning of the universe and the reason why we see these particular initial conditions. But as scientists, we want to understand whether it's true or not. And I will try to tell you the status of this question and the status of the answer. Okay. What do we know? Well, we know quite well. I mean, we know the universe quite well. So we know the composition of the universe, how many baryons there are, cold dark matter, how fast it expands. So we know what the universe is made of, okay, with good precision. This we know. Then we know that these initial perturbations are really of primordial origin. Let me explain what I mean. I mean that the initial conditions were already there when the CMB was emitted. So it's not something that emerged later on. So they were already there. And the reason is the following. So if this is the temperature polarization correlation in Planck. The details are not so important, but what I want to stress is that the argument I was giving before, so the fact that there cannot be any information going from this blob to this blob, if this is true, then you should not see any correlation beyond this gray area. So the fact that we observe very nicely this correlation over here, it means that there is correlation between points that supposedly they should be not causally connected. So this is something that we observe. There's no doubt about this. Okay, so we know that these perturbations are already there before photons can come to us. Then let's try to characterize these initial perturbations. So how do you characterize? Well, first of all, you want to know how big they are, but I already told you, because I told you that the typical fluctuation in the CMB is of order 10 to minus 5. So this is the RMS fluctuation. So the spectrum is the square of this. So it's of order 10 to minus 9. Okay, so we know this number very well. So we know these perturbations, how big they are. Then another thing that you can ask is, so now you have fluctuations, and in a Fourier decomposition, you have fluctuation at short scales and long scales. So you can ask, how do these fluctuations depend on scale? Okay? And let me explain how do we measure this. So I told you that these oscillations, they have to do with the plasma. So we understand this very well. So let's forget about this. Let's go back and understand what are the initial conditions that give rise to this oscillation in the plasma. Okay, so we're talking about. So if you get rid of the effect of the plasma, you go to the initial conditions, you find something which is very close to an horizontal line in this plot. Okay? This horizontal line is what in cosmology is called a scale invariant spectrum. It means that in real space, the correlation between 2 points is a logarithm. Okay? In Fourier space, is 1 over k cube, is a logarithm. So in some sense, it's telling you that there is correlation at all scales. Okay? What we observe experimentally is something which is very close to be horizontal, but with a small tilt. This is called a tilt, so it's parameterized in this way. The tilt is small, and it is of order few percent, with errors which is not compatible with 0. So we observe something which is not scale invariant, is slightly tilted. Okay? This, I think, it's a very remarkable hint for inflation. Why? Because, let me try to explain that this is very connected to the symmetries in inflation. So I told you, so this is a bit more technical, but I just want to convey that if in inflation you have a constant energy density, then the solution for the expansion of the universe is what is called the de Sitter space, which can be written in this form. So this is a very symmetric solution. It has a lot of symmetries. It's a solution with a lot of symmetries. And in particular, it contains a symmetry which is called the scale invariance, which, as the name suggests, implies that the spectrum should be horizontal. Okay? So the message is that in the limit in which, during inflation, you have a constant energy density, you should expect, by symmetry, that the spectrum is horizontal. It's not exactly horizontal. Why? Well, because I told you that this is the picture that I want to describe. This picture, there is a constant energy, but at a certain point, I have to finish this period of inflation. Okay? So I need to put some tilt to this potential, otherwise I will be stuck there forever. Okay? So the message is that this was observed a few years ago by Planck, these measurements. And this measurement is considered a quite good indication that we are on the right track, because again, the expectation was that the spectrum is close to scale invariance because of the reason I explained, with small deviations, and we observe these small deviations. Okay? Now, of course, how small it should be, it becomes a bit more model dependent, but at least qualitatively, we were expecting to observe this, and we did it. Okay? So this, I think, it's a good piece of information. Okay, so this is what we see. Let's discuss what we don't see. Well, as I said before, we don't observe any fluctuation in the composition of the universe, in the sense that in the initial conditions, the ratio among different species, like baryons and photons, is the same in all directions. Okay, let me not comment on this, although it contains, it has piece of information. Let me talk about gravitational waves. Okay. Why I want to talk about gravitational waves? Well, I told you that the story is that during inflation, if I have a field, this field will be excited because these harmonic oscillators will be influenced by the expansion of the universe. Okay, for sure we know that there is a field which is there during inflation, and it is the gravitational field. Okay, so these are gravitational waves. Let me stress that now gravitational waves are very popular. I'm not talking about, of course, gravitational waves produced by black holes, by astrophysical objects. I'm talking about gravitational waves which are called primordial. Gravitational waves which are produced, maybe, during inflation. Okay? So this is a very general prediction of inflation. So if inflation took place, also gravitational waves should be excited. So for this, I need glasses which are new, are polarized glasses. And the reason is it's sort of easy to understand. So the gravitational waves are basically similar to electromagnetic waves, but they have an extra index. Okay, so it's an object with two indices. It's not a vector, but it's a tensor. And well, without entering into details, but the presence of gravitational waves leave some imprint in the polarization of the light coming from the last scattering surface. So we don't only observe the temperature in various directions, we also observe the polarization. The polarization is there even in the absence of gravitational waves, but if the gravitational waves are present, there is a particular pattern, which is called B-mode, which is typical of gravitational waves. It has to do with the fact that they are not scalar perturbations, they are tensor perturbations. Okay? So there is a very large experimental community looking for this signature in the sky. So far, we only have upper limits. So, okay, this is a busy plot. I just want to say that there are many experiments. They are trying to push down these limits. So actually, what we are trying to measure are these dashed line over here. So this is some contaminant that I don't want to talk about. Anyway, it's a very challenging experiment. We're talking about a very small signal, but it's very, very, very important. There is a huge experimental effort. So how you can study these B-mode polarizations? Well, you can try from the ground. So you can do telescopes, for instance, you put them in at the South Pole because there is no humidity, so there is no water contamination. You can try using balloon experiments, or you can send satellites, which of course are very clean from any contaminant of the Earth. At the moment, okay, sorry, I'm not making justice to many experiments, but just to simplify, there is a very important experiment at the South Pole, which is this Keck-Bicep collaboration, which is at the moment has the best constraints. And in the future, there will be an experiment led by Japanese colleagues, but there is also an interesting collaboration of INFN in this experiment that will try to observe, improve, or detect gravitational waves in using this B-mode polarization. So here I said that at the moment the bounds are about 5%. What I mean? I mean that we observe these fluctuations due to the inflaton fluctuations. There are also fluctuations due to the tensor modes. The tensor modes are small, are below 5%, and these experiments promise to push these by almost 2 orders of magnitude. Okay, so to get to 1 per mil ratio between scalar and gravitational waves. So this slide is a bit technical. I just want to say that, so these are gravitational waves. This is the fluctuation of the inflaton, the one I was describing before. The ratio between these two predictions is this parameter epsilon, which is related to the tilt, to the tilt of the potential. So it is predicted by inflation that scalar perturbations are larger than tensor, and this is okay. In fact, we don't observe tensors, but at a certain point we should observe them. Of course, unfortunately, there is no prediction in the sense the number is model dependent. And it depends on the details of this potential. And at the moment, the bound is this, between the ratio between tensors and scalars, led by this collaboration. And we hope to get to 0.001 in the future. Of course, detecting gravitational waves well, will be a very, very important step because, as I said, it's a very simple prediction, okay? So if there is inflation, gravitational waves must be produced. Of course, they must be produced with a scaling variant spectrum. We know all the features that we expect. And if we observe this, is another important point. Not only that, not only as a proof of inflation, but also because observing gravitational waves will fix the energy at which inflation occurs. Okay? Observing only scalars, there are too many parameters, so we cannot fix this. But if we observe gravitational waves, we're going to know that inflation took place at a certain energy. And this energy is extremely high, is of order 10 to the 16 GeV, if we observe them. If we don't, we only have upper limits. But if we observe gravitational waves, we know that inflation took place at energies which are many, many, many orders of magnitude above the accelerators. So LHC is working at 13.8 TeV, so 10 to the 3 GeV. So we're talking about 13 orders of magnitude above this. Okay, let's hope for this. The last topic I want to touch has to do with even more sophisticated kind of glasses with 3 lenses. I was surprised to find this image on the web. I was not. So it has to do with what is called departure from Gaussianity. Okay? So I have this map, and one thing that I can check. So far, I talk about these harmonic oscillators, and when I say this, I assume that each harmonic oscillator is independent of the others, okay? Which is the same as saying that I'm talking about a free theory. Okay. It turns out that, of course, one can check, so I can look at this map, look at the various Fourier modes, and ask whether there is a statistical correlation between different Fourier modes. Okay? So it's the same as saying that at the beginning I study free fields, and then I study interactions in which different Fourier modes talk to each other. They interact with the others. So surprisingly, or not, I don't know, but this is something that we know extremely well. So we take this map, we have many, many pixels, about 10 million pixels, something like this. And we can check whether everything is compatible with the Gaussian statistics, and the answer is it is compatible. Okay? So we know very well. So if you, so we know that our initial conditions are very close to a Gaussian statistics with corrections which are between 10 to minus 3 and 10 to minus 4. So we know it super well. Okay? So more precisely, the bounds. The bounds are using exactly this map. You can get bounds which are of this order. Okay, so extremely small numbers. In the future, this number will improve, most likely not using the CMB, but different data coming from the distribution of galaxies in the universe. For instance, the Euclid experiment, DAISY, and so on and so forth. Okay, so there is also room for the improvement of this. So to conclude, so why this is an important measurement, and what can we learn? Well, the reason I told you that deviation from Gaussianity means that the theory is not free. But I told you that in order to have slow roll inflation, I need this potential to be very, very flat. Okay? So flat means that if I expand this in powers of phi, all derivatives are very small. And this is the same as saying that the theory is approximately free. Okay? So there is this consistency. So I want a flat potential, which means that I do not expect interaction among different Fourier modes. And indeed, experimentally, I see that there is no evidence of necessity of deviating from a Gaussian statistics. So everything is consistent. Put it in another way, compared, for instance, with the Higgs, which is another scalar particle, okay, which of course we know very well. So this we can measure it at LHC. The quartic coupling of the Higgs is extremely small, so it's much smaller than 10 to minus 10, while the Higgs has a quartic coupling which is of order unity. So this just to tell you that it's extremely weakly coupled compared to the Higgs. Of course, this holds in the simplest models of inflation. There are many models in which non-Gaussianities are larger, and they are constrained by the limits that we have. There is a lower bound, so FNL basically cannot be smaller than 1%, basically because at a certain point there is something which is non-interacting, which is gravity. So if you just look at gravitational interactions, you get a lower bound on this parameter. Of course, we are quite far, because the present bound are of order 5. They will become maybe of order unity in few years, but we are still very far from this number. I don't know if we are going to get there. Of course, this is really a lower limit, so this is something that is there, and if it, I don't know. But I stress this because in the case of gravitational waves, we don't have a lower bound. So if we are unlucky, we can go on doing the experiments and nothing happens. This is something that there is a lower bound. It's far, it's difficult, but at least it exists. So I'm done. I just want to leave with maybe a more, so you can ask, so I told you about quantum mechanics, but can we really test the fact that these perturbations are really quantum mechanical in the sense of doing something like Bell's inequalities? So, Bell's inequalities are inequalities that really show the quantum nature of reality. I don't think so. I don't know, but it's an interesting thing to think about. Technically, the reason is that the state of the primordial perturbations is what is called a very squeezed state, so that it's very difficult to distinguish this state from a classical probability. Okay, so it's very difficult to do to imagine some Bell-like experiments to test the quantum nature of these perturbations. Okay, but this is something to think about. So I'm done, and I leave the conclusion for you to read. Thank you very much.
So thank you, Paolo. Any question? Yes.
Thank you very much for the talk. So these models are nonlinear equations. I'm thinking about the classical models, nothing about quantum mechanics. So I'm expecting that by studying the nonlinear character of this equation and looking into the attractors, you can figure out if there is some information that can help to decide about the initial condition. For example, if the model have attractors that are strange attractors or closed orbits, I'm expecting that the issue of the initial condition is going to be much more complicated, because maybe we are inside one of these closed orbits. So then my question is there a way that I can rule out this possibility?
Okay, so it's a very nice question. Okay, so first of all, I didn't mention this, but it's important. So classically, forget about quantum mechanics. Classically, the equations, so these are coupled equations between the inflaton and the gravitational field, so the metric. So these are these equations. They are an attractor. In a sense, sorry, the inflationary solution is at least locally an attractor. So I should have mentioned this. So this is the reason why we sort of like this picture. Then we can discuss how large is this attractor, but at least it's a local attractor. So if I start sufficiently close dynamically to this solution, I'm driven to this attractor. Basically, the reason is that, well, I should not, I mean, okay, I can explain, but locally it's an attractor. Now, There is a more sophisticated question that I actually worked for a while without much of a success because I'm not a mathematician, but even with mathematician colleagues. So we can ask something more sophisticated, which I think is very interesting, which is questions of the following form. So forget about quantum mechanics once again, but can we characterize how wide is this basin of attraction? In a sense, if imagine that I start with a very complicated metric, can I argue that I will always end up in inflation? There is some indication which is probably the case, but okay, what we could do is to prove this assuming additional symmetries. So not for a completely generic initial conditions, but assuming that there is still some residual isometry. But you're right that there is an interesting mathematical problem that has to do with, yes, under which condition you can prove that you always evolve toward this inflationary solution.
Other questions? So I don't know if there's somebody on Zoom that, no question. Okay, so if everyone is satisfied, as I promised, it was very clear, so that's why.
Or not, we are not going to know, but anyway, I am around until tomorrow lunchtime, so if somebody has questions or wants to chat, I'm around.
Okay.
Thank you for listening.
Thank you.